Good afternoon, ladies and gentlemen. Welcome to my presentation. First of all, thank you very much to all participants. My name is Alper Celik. I am participating from Turkey. I am a research assistant at Erzincan Binali Yıldırım University, Department of Civil Engineering, and I am a member of FIB Young and CTE. Today, I would like to talk about cyclic loading test on highly corroded reinforced concrete columns. If you look at the presentation outline, my presentation is in 5 parts and it will take about 10 minutes. Firstly, I am going to talk about significance of this experimental study, and then I will briefly explain test specimens and accelerated corrosion method, and then I will explain used loading test setup and cyclic loading test. End of my presentation, I will briefly discuss test results and conclusions. Now, let's look at the significance of this study. Why did we need to perform such an experimental study? The first reason was empirical models for assessment of seismic performance levels of corroded reinforced concrete columns are still needed. The second significance of the study, lack of study for highly corroded reinforced concrete columns. As you know, there are many empirical models in the current literature, but these models limited to maximum corrosion level of 20%. This study was carried out at higher corrosion levels compared to previous studies. The third and main significance of this study, there are some contradictions regarding to displacement ductility ratio of corroded reinforced concrete columns in the current literature. Contradictions on the displacement ductility ratios can be explained as follows. According to some researchers, Meda et al., Gu et al., and Lee et al., as the corrosion level was increased, the ductility ratios increased, but energy capacities decreased. According to Young et al., as the corrosion level was increased, the ductility ratios and energy capacities decreased. According to Ma et al., as the corrosion level was increased, the ductility ratios and energy capacities increased. This experimental study was conducted on a total of 5 reinforced concrete columns. The specimens had same sectional and material properties. The cross-sectional area of the specimens was square and its size was 300 times 300 millimeters. The compressive strength of the concrete was 15 megapascal and the reinforcement layout shown here. In this study, an accelerated corrosion method was used to corrode the reinforcement bars embedded in concrete. As shown on figure 2, the copper wires were tied each reinforcement bar. This application is positive terminal for accelerated corrosion setup. In this study, a full-scale corrosion pool was used for accelerated corrosion method. To corrode the steel bars, positive outputs of the adjustable power supplies were connected to extended copper wires, and negative outputs of the power supplies were connected to stainless copper plates that were surrounding the corrosion pool. Voltmeters were connected to each specimen to record the current at 60 seconds intervals in order to monitor and achieve the designed corrosion levels. The theoretical mass loss was calculated according to Faraday's law. A total of 3 hydraulic jacks were used in loading test. Lateral cyclic load was applied by a hydraulic jack with capacity of 60 tons. Axial load was applied by 2 hydraulic jacks with the capacities of 100 tons. Axial load ratio was 0.4 and constant. The roof displacement was measured by a LVDT with the capacity of 200 millimeters. Now, let's look at the loading history program. The experiments were performed with displacement controlled. The loading history followed the standard test procedure for full-scale moment-resistant elements as defined by FEMA 461 codes. The loading history program is shown on Figure 5. Test results were analyzed under 4 titles: actual corrosion levels, load displacement relationships, energy dissipation capacities, and damage and plastic hinge lengths. This is one of the most important parts in this study. Our research team spent huge efforts to obtain the actual corrosion levels. After the loading test, all corroded reinforced concrete columns were broken and each reinforcement bar was extracted to obtain the final masses. In other words, obtain the actual corrosion levels. Actual corrosion levels at each longitudinal bar, actual corrosion levels at each stirrup, and actual corrosion levels at positive and negative loading direction were obtained by the way. Figure 6 shows that breaking the columns, and Figure 7 shows that extracting reinforcement bars, respectively. Extracted longitudinal bars and stirrups were cleaned by brushing. After the mechanical cleaning, reinforcement bars were reweighted with a balance of 2 load cells for determination final mass losses. Figure 8 shows that cleaning corroded reinforcement bars, and Figure 9 shows that reweighted the corroded reinforcement bars. Actual corrosion levels were calculated for each longitudinal bar and stirrup. The average corrosion levels were shown that under figures. Figure 10 shows that corrosion levels distributions of longitudinal bars, and Figure 11 corrosion levels distributions of stirrups. Load displacement curves were idealized and determined yield and ultimate loads. Green points shows yield loads and yellow points shows ultimate loads. Corrosion levels of longitudinal bars and stirrups shown on load displacement figures. Also, corrosion levels of longitudinal bars for positive and negative direction shown on figures. As an overall, if you look at these figures, the number of cycles, in other words, energy capacities decreased as the corrosion levels increased. Idealized load displacement results were summarized in this table. Yield and ultimate load carrying capacities, ultimate energy absorption capacity of corroded reinforced concrete columns decreased significantly as the corrosion levels were increased. As you can see, there is no significant relationship between the displacement-based ductility ratio and average corrosion levels. For example, the average corrosion level was 0% and determined displacement ductility ratio was 3.5 for the RC1 column. When the corrosion levels was 15%, determined displacement ductility ratio was 2.5. When the corrosion levels increased and it was 20%, the displacement ductility ratio was 5. The cumulative energy dissipation capacities at yield, maximum, and ultimate load were calculated with the area of underload displacement curves. As shown on figure, energy capacities at yield, maximum, and ultimate points were decreased as the corrosion level was increased. As shown on figures, the measured plastic hinge length was increased compared to the uncorroded one. with the effect of reinforcement corrosion. Buckling on longitudinal bars was observed due to the degradation in confinement effect caused by high corrosion levels. The conclusions of this study can be summarized as follows. Structural performance of corroded reinforced concrete columns were decreased significantly as the corrosion levels were increased. In order to accurately predict the seismic performance level of corroded reinforced concrete columns, energy-based models are needed to be developed. There is a strong relationship between average corrosion levels at longitudinal bars and stirrups. Considered average corrosion levels at longitudinal bars provide to reflect the effects of confinement by stirrups on structural behavior. Thus, the average corrosion level of longitudinal bars should be considered in the models to be developed. Among the earthquake indicators of structural behavior, present study well agreed with Lee et al. And Yalchiner et al. Where the energy-based method provides superior results to define the degradation of corroded reinforced concrete columns. Thank you very much for your interest. You can send email for any questions. Thank you.